Alright, welcome to the beginning of the new chapter, chapter 3. We started off with a worksheet on sine and cosine graphs, and they asked you to graph them first every 10 degrees. So plug into your calculator sine of 10, sine of 20, and so on. And do that for the first 10 or first 90 degrees and see how the graph looks. And then after that, it said do it every 90 degrees to see where it is. And once you have that, you can see the general shape of the sine graph, and then do that again for the cosine graph. So this says y equals cosine of theta. In your calculator, you just type in y equals cosine x. Question 3 says find sine of 45 and cosine of 65. Show that the corresponding points on the graphs in problem 1 and 2 respectively. So sine of 45, this is the sine function. If I looked at the sine of 45, 10, 20, 30, 45. And then if I go over, it looks like that's at, since this from here to here is 1, we could see that this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, a little over 0.6. So let's say it's about, let's say sine of 45. Oop, apparently I can't write well right now. Try this again. Sine of 45 is about, let's say, did we say 6, 2? And if I look at the cosine of 65, now I look down here, 10, 20, 30, 40, 50, 60, 65 is there somewhere. So I'll go straight up, and then I'll go over. And that looks like it's 0.1, 0.2, 0.3, 0.4. So looks like it's about 0.4. Now on our calculators, we can check to see if that's correct. We can press sine 45, and I'm off. It's supposed to be 0.7. And cosine of 65, it says 0.42. Here we got 0.4. So using this graph, it's not going to give you the most exact answers, but it gives you a general idea. For number 4, it says find the inverse trigonometric functions for inverse sine of 0.4. So let's go up to sine. Inverse sine of 0.4, we can go 1, 2, 3, 4. I go over, and I go straight down. And I would guess that that would be somewhere around 10, 20, 26 degrees. So I'll say the inverse sine of 0.4 is about, I know I forgot what I said. About 40 degrees? No. 10, 20, a little over 20, 26 degrees. About. Now if I want to take the inverse cosine of 0.8, let's try this. 0.8 is right there. Oop, that's not straight. We can just say that that's there. We go down. That looks like it's 10, 20, 33. So we'll say that's about 33 degrees. Now if I check those on my calculator, I'll do the inverse sine of 0.4 is about 23.5. That's close. Inverse cosine of 0.8, that's 36.8. So they're close. They're not the most accurate, but they work. Question number 5 says find the ranges for sine and cosine. Remember, the ranges are the y values. The minimum value is 1 or -1. The maximum value is 1, and that's the case for both of them. So it's between -1 and 1. You could write it like that, or you could say y value has to be between -1 and 1. Now plot the graph of this transform function y equals 5 cosine of theta. What is the amplitude of the function? So here's this graphed already. So the amplitude is how much it increased. So the amplitude of the function is 5. What is the relationship between the amplitude and the vertical dilation of the sinusoid? Well, the vertical dilation is the amplitude. Question number 3. It says, what is the period of the transform function? What is the period of the function y equals cosine of theta? The period is how long it takes to complete one cycle. And I don't have these marked, but that's 360 degrees, and this one is 360 degrees. So the relationship between these is it doesn't change the period if we change the amplitude. Now plot the graph of y equals cosine of 3 theta. What happened to the period of the function? How can that, so if we take a look at this, now this is again 360. Now we have 1, 2, 3 cycles in that time. So now the period of this function has switched to 120 because it takes 120 degrees for it to start repeating its cycle again. So how is the 3 related to the transformation? This is a horizontal shrink by a factor of 3. How could you calculate the period using the 3? Well, it's usually 360 degrees, and we're going to divide it by how much we're shrinking by to get the period of 120 degrees. Plot the graph of cosine of theta minus 60. What transformation is caused by that? Well, if you plot it, you probably don't even need to plot it to be able to see that this just moves it to the right 60 degrees. Question 6. The theta minus 60 in problem 5 is called the argument of cosine. The phase displacement is the value of theta that makes the argument equal to 0. What is the phase displacement of this function? We call that phase displacement right there, so that would be 60, because we go 60 to the right. How is the phase displacement related to the horizontal translation? That 60 degrees is what we translate to the right. So if this is our regular cosine graph, our new graph is just going to be translated over 60 degrees. So instead of this being 0, now that right there is 60 degrees. Question 8. The sinusoidal axis runs along the middle of the graph of the sinusoid. It is a dashed center line shown in figure 3.1a. What does the transformation of y equals cosine of x function does to the location of the sinusoidal axis? So if we take a look at this function here, that moves that up 2, because you can see now that that's the sinusoidal axis. So that plus 2 just moves the sinusoidal axis up 2. Question 9. Suppose that y equals 6 plus 5 cosine of 3, parentheses, theta minus 60. What are the amplitude, period, phase displacement, sinusoidal axis location on this graph? So we'll start with amplitude. Amplitude is going to equal 5. That's your vertical stretch. Your period is the tricky one because we shrink by a factor of 3. So 360 divided by 3 is going to be 120. The phase displacement, we're moving 60 to the right, so that's 60. Sinusoidal axis. The sinusoidal axis, we're moving it up 6. All right, now we have an exploration for you to go through. So take your time to go through it, do the best you can. The first problem just tells us to graph these months. Question number 2 says the graph of y equals cosine of theta completes a cycle in every 360 degrees. Angle, not temperature. What horizontal dilation factor would make it complete a cycle in 12 degrees, as shown? So instead of going from 0 to 360, we're going from 0 to 12. So what we have to do is take 360 divided by 12, and that would give you 30. So 30 is going to be the horizontal dilation factor. So the equation of this graph would be y equals cosine of 30 theta. The Earth rotates 360 degrees around the Sun in 12 months. How do these numbers relate to the dilation factor in problem 2? Well, the 12 months represent how, 1 year, so each year the temperature patterns are just repeating again and again. The temperature temperature graph in problem 1 has a high point at x equals 7 months. What transformation would apply to the sinusoid in problem 2 to make it have a high point at theta equals 7 instead of theta equals 0? So that would make us move the graph to the right 7. So let's start with our graph from before, or an equation from before, 30. Now we're going to take theta and we're going to move it to the right, so that has to be minus 7. The average of the highest and lowest temperatures is 78.3. Write an equation of the transformation that would translate the graph in problem 4 up 78.3 units. So we'll have y equals 78.3 plus cosine of 30 theta minus 7. So that moves it up 78.3. That shrinks it by a factor of 30, and we move it to the right 7. The 94.9 high point in problem 1 is 16.6 units above 78.3, and the 61.7 low point, 16.3, is 16.6 units below 78.3. Write an equation for the transformation that would dilate the sinusoid in problem 5 by a factor of 16.6, so it looks like this graph. Confirm your answer by your grapher. So we're going to vertically stretch it 16.6. So we're going to start at 78.3. We're going to stretch it 16.6 up and down, and we're going to shrink it by a factor of 30, and then we're going to move it to the right 7. All right. Now try this out on your calculator to make sure you graph this correctly. On your calculator, your calculator gives you this, so you have to finish the parentheses off like that. So when you're doing this in your calculator, you need an extra set of parentheses. And that's the end of today's lesson.